Hello everyone, this is Dr.Hira, and now we will talk about the basic concepts of the organic chemistry. In the previous lecture, which was about the general introduction about organic chemistry and organic compounds, we have seen and we have defined what the organic chemistry is and how the organic compounds are. So one thing which we have established, and we know that the organic compounds are basically the chemistry of carbon based, and they have the other elements, hydrogen, nitrogen, oxygen, but majorly they are on the carbon and hydrogen based compounds, and they are covalently bonded to each other. Now in this lecture we will cover the basic concept that how the elements are instigated to form the bonds, the covalent bond in that scenario when we're talking about the organic chemistry. And secondly, we will see how what is the electronic configuration an element is going through for making a bond. And we'll talk about the very important topic, that is the hybridization. And this is under the bonding, a special scenario when an element is making itself for the bonding, and it is establishing some kind of modification that it goes through the hybridization to make the maximum bonds. Let's start. So the very first question which came into mind is, what instigate actually elements to form the molecules? For this, I need your attention that if you just see your life and our daily life, that we all have some aims in our life, and we all want to settle in our life. We want to achieve a certain position where we have the good money for our needs, for our desires. We have a position, we have the aim for our life. We achieve for that. For example, I wanted to be a professor of chemistry. So that was my destination, that was my aim. And from being a kid in a preschool or in a first school or maybe in a school later, that were my desires. So I have to go through that procedure, I have to take that steps, baby steps, and then the big steps to be at the position where I am holding the position where I am. So I'm a professor of chemistry, right? I'm teaching the chemistry. So here the thing is that that was my goal. So the elements also want, and the universe is basically the collection of the element, right? So the elements are basically have the desire to complete and to get their ideal configuration. So that's why they are making the bond, and that motivation and that aim is basically that they want to acquire the noble gas electronic configuration. You know about the periodic table, you know about the noble gas, the eighth group elements, which are the inert one, which are in a position that they have achieved everything. They have 8 electrons in their outermost shell, except the helium, because helium is the smallest inert gas, inert element, and this is having the 2 electrons in an outermost shell. I'll see in the next slide that every period element have their own ideal, have their own um, ideal gas for achieving the electronic configuration. Currently we will talk about the carbon. So we are concentrating on the second group electronic configuration, right? Which start with the lithium and then ending at neon. This desire of elements basically to complete the octet. Octet means to having the 8 electrons in the outermost shell, results in bonding with other atoms to create compounds, diverse and complex compounds, mixing and overlapping of electronic orbitals. So the points which I have mention these under this, the desire of element to complete octet results in, is basically the procedure, the process, the modification the elements are going through to achieve their destination, right? Whenever we are struggling and we are moving from A step to Z, which is we require. So we uh, go through the different modification, we improve ourselves, we learn so many things. So that is also creating a lot of things. So as in an effort to be a chemistry instructor, to be an advisor, to be a professor of chemistry, so I go through the research, I learn chemistry, I learn English, I learn experiment experimenting, I go through the literature review, I see the paper publications, I travel a lot for the conferencing, for networking. So proposal grants and how to set the chemicals, how to set up research projects. So these are the things basically which in a process you are gaining a lot of things, and these are also creating and these are also contributing a lot of things. So when that is the ultimate aim, that they want to acquire the octet, electrons are elements are going through the different combinations, they are going to the different bonding. So that has enabled scientists and the chemists to see, to study these principles. And then there is a lot of things in a chemistry which has helped us to develop our own synthetic materials, right? So if you just look at on the electronic structure of the atoms, so simply what the electronic structure is, that this is in a periodic table, this has place on the basis of their atomic number. And here you can see this hydrogen and its ideal is the helium here. And the second group starting with the lithium and ending at the neon, and the carbon belongs to the second group period, but the fourth group. So fourth group elements have the four excuse me, four electrons in the outermost shell. And this is basically the upper principle description, that how these orbitals will be filled and what are their energy level positions, and the electrons will be placed there, right? So you should remember this one. This is the S is the orbital, P is an orbital, D and F are the different orbitals. And around the nucleus, if we just go for next slide, so around the nucleus, they are the probability of the electron finding, and that is called termed as a shell and an orbital. So you should need to see the difference between a shell and an orbital. A shell is a region of space around a nucleus that can be occupied by electrons corresponding to a principal quantum number, right? So either that is the principal quantum number is the um, um, 1, 2, or 3, right, on the basis of that one, and this is basically the major. So you can see that if you are talking about a building, so the shell is somehow, it is giving you the idea about the floor, right? Is it a ground floor, first floor, second, or third floor? Now the orbitals is basically just an example of a building. It is a room in each floor. So in a shell, we have the subshells and the orbitals. So orbital is basically a region of space that can hold two electrons. So this is just defined with the maximum of the two electron an orbital can hold, and this is the most you can say the most specified space for the electron probability. And then on a larger scale, that number of orbitals are mixing, are sharing the same floor, so they comes under the shell. So now there are the two terms, what is a ground state electronic configuration and excited state electronic configuration. So you should know what the electronic configuration is, means that, as I told you, that the protons and the neutrons, which are the particles of the atom, they are concentrated on a nucleus. So they are not coming out of the nucleus, and they are not involved in a chemical reaction. So you have heard about the nuclear reactions. You have heard about the fission and fusion. So these are the processes where the element is hit from their nucleus, right? So these protons are then came out. So it means in that scenario, this is loss losing its identity. So this is no more the same element, because it's the main core, its nucleus has hit, and that has damaged or destroyed, in a literal or in a layman language, right? But when the electrons are involved, so they are basically the kind of particle which can add, which can remove, without losing the identity of an element. So that is basically the atomic structure, right? And here in that carbon atomic structure, I have shown only the shell, not the orbitals, right? So this is the K shell and this is the L shell, right? And the ground state electronic configuration is basically which an element is having, and how the electrons are arranged in its very normal, subtle, and non-reactive um, form, right? So this is called as the lowest energy electronic configuration. So how it is when you are not providing any heat, you are not providing any light or any radiation, or there is no other element which can instigate it to form a bond. So in a normal condition, the ground state electronic configuration is how we will allocate the electrons. Excited state electronic configuration is the high energy than the lowest energy electron configuration of an atom or a molecule. So an element go through for shift from the ground state to excited state electronic configuration when it is sensing and what is seeing that there is something which is offered in an environment, and it can make a bond, and that can now it can be in a ideal configuration, or now it can be in a more stable form, right? So then it will get excited. So this is just like this one, that once you have you are waiting in a normal way, you are just starting and learning, and eventually there came an opportunity, that is opportunity is there, that you are getting some of the fellowship, or maybe some of the study grant you are having. So you will get excited, and then you will work on it, that how I can get into that, and definitely that would be the plus point in your career, in your study, that you will go for your desired destination. So similarly, in a way, the electron elements will go for the excited state electronic configuration. So then we will establish here in the carbon case. Now firstly we will just discuss that the carbon atomic number is 6, and it means it is having the 6 electrons. Atomic number is giving the information about the number of electrons or the number of protons. So we exclusively take into account more on electron side, because we are dealing with the chemical reactions. So we'll talk about the electrons. So this is giving you the information that there are the 6 electrons in the carbon atom. So how you will place these in the orbitals, and how you will configure these electrons. So this is, you should remember that this is the 1s, 2s, 2p, and these numerical values 2, 3p are basically giving you the idea that what is the energy. So higher the number, it means they are the high energy orbitals. So when you are placing these electrons, so you will always go for the low energy orbitals, and then you will start move for the higher, and then you will start the pairing up. So we will define that one. So here, this S is basically the one shell. I can mention you with the pen here. So this is basically the K, which is having only the one orbital, and this P and S, 2s and 2p are is basically making the L shell, right, which is a second shell, as you can see in this diagram. So here, this S is K is having only the one orbital or only the one subshell. So an orbital can maximum have the 2 electrons, right? And numerical notation that you could guess that how many number of electrons will be there in an orbital based on their principal quantum number is the value is 2 and 2, right? So for the K, the value, the principal number, quantum number is 1. So it means there is the 2 right? And if we solve that one, so the value is n is 1, right? And scaring, taking the square of 1 and then multiplying with 2, we will get the 2, right? So this is giving you the information for that a shell can accommodate how many maximum electrons. So orbital can accommodate maximum 2, but for the shell, we can calculate by this fraction that 2n square is giving you the idea that how many total number of electrons will be there in a shell. So if this is a shell 1, this is a 1 s, right? So it is 2 if there will be the 2, so taking the square of the 2 is will be the 4, and 4 into 2 will be the 8, right? So in an X there will should be 8 electrons in the outermost shell, right? So in carbon the shell L is the outermost shell, so that's why it is in a desire to complete it with the 8 electrons. So now we will place this electrons in that way. There is a correct and there is incorrect way how we can do that one. So firstly you will go for the lower energy. One is the lower than the second one. So we will place these electron and we will pair it up. We will accommodate the maximum 2 electron of that orbital in opposite spin to balance that one, because they do, both electrons have the same charge. So they have the maximum repulsion. So when they are in opposite spins, they can be balance that configuration. Now the 2s, in this shell, there is S subshell and there is a P. So the P is in the spatial rearrangement has a PX, PY, and PZ, right? So what we will go through is the firstly you will place electron in a 2s. It is the lower than the 2p orbital, a little bit lower, but there is a huge difference of energy in the 1s and 2s, and there is energy difference, but this is little as compared to this difference. So these three are the degenerate orbital, that's why they have put it in a bracket. So they are of the equal energy. So for the equal energy orbitals, we always go for the single allotment of the electrons, and then if there are still the electrons left, so then we will start pairing in the opposite direction. So here the correct electronic configuration of the carbon is the 1s2, 2s2, and 2p. We have only left with the 2 electron, because in a total the carbon has a 6 electron, so there is 1 with unpaired condition. And if you will pair this up one, so this is incorrect, because for the same energy orbitals, we will put them firstly separately, and then if we still have the more electrons, we will pairing up. So why it is so? So you can just take an example it from your from that if we have to allocate building floor, so it would be the desire that we can occupy the more number of rooms, so then we can have the more sharing, right, rather than the pairing up with that one. So then we can accommodate the more of our group. So that's why this is unpaired electron allotment in the same energy level orbitals, and then when there will be the new electrons, so they can accommodate with that one and they will have the maximum bonds. So now this is a check post task, and you just have to go for this, that write the ground state electronic configuration for each element showing the occupancy of each p orbital. Occupancy of each or p orbital means that you have to write in detail, not the simplified version as we did. This is the with the p occupancy, and this is the simplest version, that sometime we just group it up as a 2p. But I'm asking that you write in detail, that you write the px, py, and pz, and you have to go for the electronic configuration of lithium, which has atomic number 3, oxygen 8, and chlorine 17. And the hint for filling up this is the Hund's rule. One rule is the Aufbau principle, and that is basically that that the low energy will be filled first and then the high energy. And the Hooke's rule states when orbitals of equal energy are available, but there are not enough electrons to fill all of them completely, one electron is put in each before a second electron is added to any. So that you have to do that task, and then we will move forward for the hybridization. Now the hybridization is basically a kind of arrangement the element do by its own self to maximize the bond and to get its desire. Sometime what is happening is that, for example, you want to have your own house, but you don't have such kind of financial, you have the financial constraints and you are not able to save money as such, or you don't have that big asset that you can go for your own home purchase or the construction. So what we will do is that you will go for some of the arrangement that can adjust, and then you can have that and you can manage yourself. And there could be the different possible ways, but the one way is that you go for the house building finance or something like who can finance your or mortgage, so you can have your own home, and with the passage of time you are managing this one and you are giving them the installments. So in that way, the elements which are not possible otherwise, that they can have the 8 electrons in their outermost shell, if they go for the ground state electronic configuration, so what they do is that they will go for some of the arrangement, and their electronic orbitals are pair up with each other to make that adjustment that they can maximize the bonding, and they can take the electrons from the other elements to fill their octet. So one the very interesting example is the carbon. So the ground state electronic configuration of carbon is 1s2, 2s2, and 2p2, right? The 6 electron fill up lower energy orbitals before entering high energy orbitals. So that is one by one. I'm just refreshing with the rules. So you are following this pattern, and then we'll see how it goes through the hybridization. So the off-work principle is this. Now the third is each orbital is allowed a maximum of 2 electrons. We already have established that fact. So this is the Pauli exclusion principle. The two 2p electrons occupy separate orbitals before pairing up, and that's Hund's rule. So the carbon, so basically the electronic configuration is according these quantum chemistry principles, and you should know what the Pauli exclusion, Hund's, and Aufbau principles are there. Now the carbon atom can mix the 2s and 2p atomic orbital to form new hybrid orbital in a process, the hybridization. Now there is a big question that why it is doing this. Why? What is the need for go through the hybridization? So here is an answer. So firstly, what is happening? That electronic configuration we have already seen that there is a 1s, there is a 2p, and there is the 2s orbital, right? And this is the ground state electronic configuration. So in that scenario, if you just look at this one, so this is the K shell, right? And this is the L shell, right? So this is the outermost shell, and we know that the carbon has ideal neon, that it could have the 8 electron in an outermost shell. Now if we just look at this one, this 2s is max filled already. So this is having the 2 electrons, and an orbital can only have the 2 orbital. We cannot enter any other electron, and that electron will come from the other element with which it is pairing. So they are sharing electrons with each other. So now if you just look at this one, this is a 2px, 2py, and 2pz. So 2pz is totally vacant. So for making a bond and the covalent bond, so there is a need that there should be a sharing. So this is a totally empty or the vacant one. So an electron or other element will not give its both electron or the electron pair to itself. So there should this carbon already have something in it in this room or in this orbital. So if the other electrons elements are pairing with that one, so if, for example, if it is making a bond with the hydrogen and we have filled this electron has been um, shared with the hydrogen, for example, right? So what is happening is that how many total electrons are in outermost shell of the carbon. Now the two from itself, this one, four was already there, and the two hydrogens are there to make the bond. So 2 to 4 and 5 6, so it is still deficient with the two electron, right? So it cannot share this with another element. So what the carbon do is that it will go for the hybridization when the atomic orbitals 2s and 2p atomic orbital are combining, they form a new hybrid orbital. So what that will do is that this s orbital can shift its electrons, will pair with that to this one, right, to fill this in that way, and there will be only one electron in 2s, right? I'm just removing for the moment here. So basically now if you just look at this one, there is the 1 2 3 and 4 electron in the four orbitals of the L shell. Now it has the four unpaired electrons. It means it can share these with the four elements. That could be the same or that could be the different one. So now it can make the four bonds, and then overall one bond means there is a pair of electron. So if it is making pair bonding with this hydrogen, and again here it is making a bond with the hydrogen, right? And here this is making a bond with the hydrogen. So sorry for, I'm just writing this hydrogen in the same picture for your understanding, right? So here 2 4 5 6 and 7 8, so here the carbon has attained at electronic configuration of the ideal gas. So that is the basically motivation that why the elements are going through the hybridization, and this hybridization is mixing or overlapping of the electronic orbitals to generate the new orbitals, and these are called the hybrid orbitals. So they have the little bit different energy than these mixing electronic orbitals. So now we will see there are the three kinds of hybridization in case of the carbon. So this is the sp3, and then in sp2 and sp. So sp3 hybridization is basically when there is the 1s orbital and the 3p orbitals, which is the px, py, pz, they all are overlapping with each other to form the four new hybrid orbitals, right? So sp3 hybridization is for four single sigma bond. When you'll see that the carbon is in a single bond with the hydrogen, that is not limited with the hydrogen. That could be it is making a bond with the carbon, but that is a single bond. It means that this is a sigma bond, right? And this is the sp3 hybridized in methane CH4. The orbital move as far apart as possible, and the loops point to the corner of the tetrahedron. So the geometry for this would be the tetrahedron, and the bond angle will be 109.5. And the example is the methane. Now the sp2 hybridization is when there are the three single sigma bonds and one pi bond. So whenever there is a double bond, so let me write in a way that you can see here. So let's say this is C double bond C. So right now I'm not just completing its valency. It is just to show you that this is a sigma bond, right? And any second uh, uh, or the third bond will be the pi bond, right? So in case of the alkenes, there is a one sigma and there is a one pi. In case of alkynes, where the triple bond, so there is a one sigma and there are the two pi bonds, right? So here in this scenario, you could see that this is a CH2 and CH2, right? So one sigma bond, and that is through the combination of 1s and 2p orbitals, right? So if you just calculate the percentage contribution for each of the hybridization, so you should know, if you just assume this a total is 100%, and if that is a scenario that s is 1 and p is 3, in the previous case that was a 75 and 30%. Now in this case this is the 2p and 1s, so that is somehow the that was is the 33 and 66, and in sp3 case this is a 25 and the 75 scenario, right? So the three sp2 orbitals point to the corner of a triangle. So this is giving the geometry for the molecule triangle. So whenever the carbon is in a sp2 or any element which is in a sp2 hybridization, so molecule geometry is this one, that they are arranged in a triangle um, geometry, right? And that is a shape of the molecule, and the bond angle will be the 120. So next is the sp hybridization. So in sp hybridization, this is through the combination of the one s orbital and one p orbital. And sp hybridization for two single sigma bond and two pi bonds. The two pi bonds require two p orbitals, and hence the carbon is sp hybridized. In ethine, CH triple bond CH, the two sp orbitals point in the opposite direction, and the geometry will be the linear, and the two p orbitals are perpendicular to the sp plane, right? So you can see here, this is the shape of this one. This is on the x-axis, a y and a z-axis. So these are the p orbitals. Now as like the unlike the sp3 where there was a hydrogen for pairing with each p orbital, because the all of the orbitals have paired up for generating hybrid orbital. Now there is not enough hydrogen with the carbon. So what is it, is only having the 1s and the p orbital which go through the hybridization, and now these two p orbitals have not involved in the hybridization, so they are just coming to the line to line pairing, and they are generating the two pi orbitals, right? So this is the front to front. So I will show you in a next lecture that how this is making the pairing up of. But at this moment, I want to establish this concept, and what the hybridization is, and what are the different kinds, and the geometries and the shapes of these molecules. So the example for this is the ethine, which is the triple bond carbon, right? Now the shape of molecule, I have told you, for a single carbon oxygen bond, the atoms are sp3 hybridized, and the carbon atom is tetrahedral. For a double carbon double bond and carbon oxygen bond, the atoms are sp2 hybridized, and the carbon atom is trigonal planar. For a triple bond carbon or carbon triple bond nitrogen bond, the atoms are sp hybridized, and the carbon atom is linear. So I have shown you with the ball and head stick model that this is the tetrahedral shape. And if you just draw the line, so this is properly the tetrahedral shape. This is the trigonal, and this is the linear. Now the bond strength and bond length is that when we have the sigma bond, right, this is basically the more longer bond. And of course, when they has the more separation between these two atoms, so this is not as strong as the double and the triple bond, because the shorter bond is the giving the this is a sandwiched one, right? So this is giving the more strength to that bonding. So the carbon carbon single bond strength is 350. 350 means that that amount of energy, kilojoule per mole, is required to that break that bond. And the bond length is 0.15, and if we will write it in the angstrom, so its value will be 1.5 angstrom, right? If you want to mention it in the angstrom, not in a nanometer, so you know the angstrom is equal to the 10 raised to power minus 10, right? In the meter, right? Equivalent to, so this nano means 9, and this angstrom is 10. So if you just convert into angstrom, so this is the 1.5 angstrom. So here you can see is carbon double bond carbon 560, and its bond length is 0.13. Carbon triple bond carbon 810 and zero point 0.2, right? So this is basically, so for the carbon double bond carbon, we need 560 kilojoule per mole for dissociation, for breaking that bond. So that is giving you the idea about the bond strength. So the triple is the most strongest bond. So that requires 8 10 kilojoule per mole for breaking that bond. So it means because the pi bond is providing a sandwiched shield around the sigma bond, so they are the short, making it shorter, and they are just the double or triple shielded bonding. So that's why this is a more stronger one. And now we will go for the next slide. This is about your task from this lecture, and you have to identify the atom that has each ground state electronic configuration, right? So this is a 1s2, 2s2, 2p6, 3s2, 3p4 is one of the electronic configuration I have given to you. So you just have to match from the periodic table that what exactly this atom is, and same is for the B. Now in the second question, some of these structure formulas are incorrect. They don't represent a real compound because they have atoms with an incorrect number of bonds. Which structural formulas are incorrect, and which atom is in them have an incorrect number of bonds? So you should have to encircle that carbon or hydrogen or chlorine or any of the atom which is making the abnormal bonding. For the hint, I could say you that the nitrogen can maximum make the 3 bonds, and you have to match with the periodic table, because now you are good enough to know that what is the electron atomic number and how many electrons are there, and if it belongs from that group. So it means that is having that outermost valence electron, so it can make that number of electrons there, right? So you have to encircle that element, and you have to mention that what is wrong with them. Either they are making the more bonds than their accepted value, or either they are under the bonding and their valency is not satisfied, right? So that's for today, and thank you. Have a good day.